Lance Armstrong, Marion Jones, Barry Bonds, just a few of the many professional athletes whose legacies are forever tied to performance-enhancing drugs, or PEDs. Athletes are constantly tested for PEDs, and in this lesson we'll look at some sample tests and say what it means for a test to be a good test or a bad test. To start things off, here's a table where the left column is athletes who used PEDs, like steroids or human growth hormone, and the other column is athletes who did not. And the top row is athletes who tested positive, and the bottom row is athletes who tested negative. So first off, calculate this test's sensitivity and specificity, or click here to review. Right, the sensitivity is 9 over 9 plus 6, which equals 0.6, and the specificity is 45 over 45 plus 5, or 0.9. So why do tests for PEDs, for disease, for prediction models, or any other tests in general, why do they even have false positives and false negatives? Why aren't the sensitivities and specificities just 1? Well, suppose you develop a new test for PEDs. When you test athletes that you know are clean and did not use PEDs, here are some of the results you get. And when you test athletes you know have used PEDs, you get higher numbers. So if another athlete comes in and you don't know if they've used PEDs or not, and their test comes in at 913, should you suspect that they've used PEDs? Right, that's a really high number, so they probably used drugs. Now, what if another athlete comes in with a score of 504? What would you say now? Right, in this case you can't really tell. 504 is less than 506, which is one of the negative samples, but it's greater than 502, which is one of the positive samples. So for this athlete, you kind of have to guess, and there's a good chance you'd guess wrong, resulting in a false positive or false negative. Another way to look at this is with a graph of the distributions of test results. Among athletes who don't use PEDs, some will have a lower test result, others will have a higher test result, and most will be in some middle range. And for athletes who did use PEDs, they'll typically have a higher test result. Now, it's up to you to determine what constitutes a positive or negative test result, and this can be tricky because there's some overlap, where it's hard to tell whether an athlete cheated or not. So where would you say is the best cutoff between positive and negative test results? Which of these lines best divides the athletes who cheated from those who didn't? Right, this is the best value for a cutoff. Any athlete with a higher number you'd say has a positive test, and athletes with lower numbers would have negative tests. Now, because these distributions overlap, this test will result in some mistakes. Consider this group over here, who did not use PEDs, but whose test results are considered positive. These are false positives, because they incorrectly tested positive. And what about this group over here? Are they true positives, true negatives, or false negatives? So now let's introduce an interactive graph, where you can choose any cutoff value you want. The true and false positives and true and false negatives are shown in the graph, and keep in mind that the two curves are overlapping. An important thing to notice is that as you sweep the cutoff from one end to the other, there seems to be a trade-off between sensitivity and specificity. Over here, the sensitivity is high, but the specificity is low, while over here, the sensitivity is low, but the specificity is high. So at this point, try placing the cutoff so that both the sensitivity and specificity are greater than 0.9. Perfect! So here's another example of a cutoff where both the sensitivity and specificity exceed 0.9. So why is there a trade-off between sensitivity and specificity? Well, as you move the cutoff line to the right, you're turning false positives into true negatives. That makes specificity go up. But you're also turning true positives into false negatives. That makes sensitivity go down. So the result is a trade-off. So for most tests, you'll choose a cutoff that gives you a pretty high sensitivity and specificity, like this cutoff here. So how can you have a perfect test where the sensitivity and specificity both equal 1? Try moving the cutoff line as well as the distributions for the two populations and see if you can create a near-perfect test where the sensitivity and specificity both exceed 0.99. Great! So here's another example of a near-perfect test. The two populations, those who used PEDs and those who did not, have very little overlap. As long as the cutoff lies somewhere between the two populations, sensitivity and specificity will both be very, very close to 1. Now, what happens when the two populations have a lot of overlap? So here's an example where the two groups overlap a lot. This makes it tougher to tell who's actually using PEDs, right? Try finding a cutoff where both the sensitivity and specificity exceed 0.8. And if you give up, click here instead. Yeah, having both sensitivity and specificity exceed 0.8 is impossible for this scenario. For a test to be a good test, the two populations should have as little overlap as possible. At this point, let's see what happens if we have two distributions and we try out every single cutoff value. Suppose our cutoff is all the way out here, and let's make a graph of sensitivity and specificity. For every cutoff value, we can plot a point of its sensitivity and specificity on this graph. So out here, since everyone tests negative, that means we have no true positives, making the sensitivity 0, and no false positives, making the specificity 1. Now, as we move the cutoff value, we have a trade-off between sensitivity and specificity. Between these two distributions is our ideal cutoff value for the test. The sensitivity is pretty high, and so is the specificity. And if we keep going, eventually the sensitivity goes to 1 while the specificity goes to 0. So this is a pretty good test. There's not too much overlap between the two groups, and we can choose a cutoff where both the sensitivity and specificity are pretty high. Now, what if we had a better test where there's even less overlap between the two groups? Again, if we choose a cutoff out here, everyone tests negative, so the sensitivity is 0 and the specificity is 1. Now, as we move the cutoff, we have a really great test where the sensitivity and specificity are both really, really close to 1. And once again, moving the cutoff way off to the left, sensitivity goes to 1 and specificity goes to 0. So this graph indicates a great test where you can pick an excellent cutoff value. Now, a really bad test would be when there's complete overlap of the two groups, and the distributions are the same, regardless of whether or not they used PEDs. For this scenario, we again start at sensitivity 0, specificity 1. And now, when our cutoff is right in the middle, half the PED group are now false negatives, and half of the clean population are now false positives. So the sensitivity and specificity are both 1/2, or 0.5. So this is the resulting graph you get, and again, this is representative of an awful test. So these graphs, where you plot sensitivity versus specificity for all the different cutoff values, get a special name. They're called receiver operating characteristic curves. That's a mouthful, so you'll often hear them called ROC curves. Now, you might have noticed that the worst test over here has the smallest area under the curve. And as the test gets better, the area under the curve gets larger, and the best test has the most area. The maximum area under the curve you can have is 1, and that's when this point is all the way up in the corner. That would be a perfect test, with sensitivity and specificity both equaling 1. The minimum area, or worst case scenario, is this one, where the test absolutely cannot tell the two populations apart. So what's this area under the curve, meaning the area of this green triangle here? Excellent! The minimum area under the curve you'll usually see is 0.5. So testing for PEDs is just one example where ROC curves and the trade-off between sensitivity and specificity come into play. You'll see these concepts all the time with prediction models, machine learning, and diagnostic tests for disease. Anytime you're evaluating a test to distinguish between groups, this kind of analysis will come in really handy and can tell you whether your test is good, great, or awful.